I want you to take a look at this reaction here, and I'm about to run that reaction right here. I've got some hydrochloric acid, and I've got some magnesium metal, and it's sitting inside this balloon here. And what I'm going to do is eventually I'll tip up this balloon, and I'll let the magnesium mix with the hydrochloric acid. And just knowing reactions like you do, you know that we're going to have some products made from these two reactants. And those products, if you look at charges and what they're going to break apart and become, we know that we're going to get magnesium chloride, right? But we have to write it correctly, and that's written correctly. And we're going to get some hydrogen gas made. All right, now the gas, why I'm using the balloon, is it should travel into the balloon and expand the balloon, and I should be able to see that. All right, and so here's the reaction, right? But it's not balanced yet. I've got two H's and two Cl's over on this side, and that's a pretty simple fix by just doing that, okay? What does that mean, though? What does that 2 in front do? It's really just a ratio. It's a ratio of how many magnesiums I need to hydrochloric acids in order to make this reaction take place. And so it's a reaction of 1 of these to 2 of these. And what will I make from that? I will make 1 magnesium chloride compound, okay? 1 molecule of that, 1 of those, right? And I'll also make a hydrogen 2. I'll make a hydrogen molecule made up of 2 hydrogens, okay? So it's just a ratio of how much of this I need compared to that in order to make this reaction take place, all right? I'm going to back out of these blues here for a second. So just imagine that we could get down to like 1 atom. Okay, imagine I took 1 atom of magnesium and I added it to 1 hydrochloric acid molecule, just 1 of them, okay? I wouldn't be able to make this product, okay? I wouldn't be able to make this product. If I'm in the business of producing hydrogen gas, okay, and I'm getting my hydrogen gas by doing this reaction here, you know, it's basically, it tells you how much of each reactant you need in order to produce that product, okay? It is a recipe, and when you look at recipes for cooking, it tells you exactly how much of one thing you need and another in order to produce your final product, okay? Whether or not that's a 9x13 lasagna, whatever, okay? Maybe it's a pumpkin pie, but you're going to be given a set of instructions. And that's what this is, this balanced chemical reaction. When I do this right there, it is truly just a recipe, all right? And it says, hey, you need 1 part magnesium to 2 parts hydrochloric acid in order to produce these products, okay? So here, like I said, I'll go ahead and pour this in. The hydrochloric acid's pretty strong, and it's going to react with the magnesium. And I don't know what's going to happen, to be honest with you. I didn't do any measurements, okay? What do I mean by that? I don't know if I have 1 part of 1 to 2 of the other, okay? I need to know how many atoms there are, right? Isn't that what this is? This is the number of atoms on either side, but I'm dealing in trillions, okay? I'm dealing with trillions upon trillions of atoms of magnesium sitting here, and hydrochloric acid molecules roaming around in this container, and so in this test tube. So because I'm dealing with trillions, I didn't do any math here. I didn't figure out how much I needed or how much I was gonna, how much hydrogen I was gonna get. All right, I have no idea what this balloon is about to blow up to. I have no idea. Okay, it could get huge. It could just kind of puff up a little bit. All right, I could use up all the magnesium. All the magnesium can convert over to magnesium chloride, and I could be left with a lot of hydrochloric acid left over. Maybe I don't want that. All right, So what we're going to creep into here in chemistry is looking at how can I really figure out the exact amount of magnesium to use to hydrochloric acid in order to obtain a certain amount of a product. All right? And so this is just basically that idea of counting atoms, just like we've been doing, and using, instead of using numbers in the trillions, using the mole as our helper, okay? Our way of counting atoms. And so here, we'll go ahead and pour this in and see what happens, all right? If I drop it and, I don't know, get sent to the hospital, you'll know because I didn't do any math first, okay? Oh boy. Okay, that got really hot. So hold on a second, I'll be right back. I gotta get something to handle that with. Okay, we definitely produced some hydrogen gas. All right. I don't want to hold this for long. I don't want it to degrade in there and pop. But the magnesium in there went quick, didn't it? Didn't take much. So hold on, I'm going to go put this down. I'll be right back. Whew. It's not safe, is it? You don't know what you're going to get when you just put a couple of things together. So, but there's a way to do that. And so it comes from this balanced reaction to see how much of one thing I'm going to get versus the other, okay? And so, again, just counting atoms, looking at these ratios of how much of magnesium is it going to take to the hydrochloric acid to make a product, okay? So just in review real quick here, I'm going to pull up an image. Take a look, okay? We've got a bunch of different either compounds or pure elements, all right? And what you're looking at in each one of those is 1 mole of each one of those substances, all right? So what does that mean? Well, this is a mole of copper. I don't know if I can, I guess I can't. I want to see if I can write. I was hoping to be able to write on this. Anyways, this mole of copper right here, what does that mean? Well, how many copper atoms are in that beaker? We know exactly how much because we know how much a mole is. All right. How did the scientists that put that in there know how much to measure out to know that they had a mole? Right? So this is the discussions we've been having. Specifically, you know, you go to a periodic table, you look up copper, there's about 63.5 grams of copper in that, all right? And what does that mean? Well, 63.5 grams, you express the atomic mass in grams, and when you do that, you know you have a mole of that substance. So what's a mole of copper? It's just trillions upon trillions of those atoms, but exactly you've got approximately 6.02 times 10 to the 23rd atoms when you have a mole of that substance. All right. Same thing with sulfur here, except that sulfur is approximately 32 grams, 32.066. If you measure out that much sulfur, you know exactly how many atoms you have. Okay. And so if that stuff is going to get used up, or this is going to get used up in a chemical reaction, you can tell, just like we're dealing, back to this real quick, 1 part this to 2 parts that, well, how many atoms are there that you know, how many atoms are there that you're dealing with in a reaction? Sodium chloride now, this is a mole of sodium chloride. What do you have to measure for that? How much do you have to put on the scale to know that you have 1 mole of sodium chloride. Well, you know, it's a little bit different than a pure substance found on the periodic table, right? Copper is easily found on here. Look up Cu. What's the atomic mass? 63.546. You measure out that much, express it in grams, and you know you have a mole's worth. But sodium chloride, you can't find sodium chloride on here. All right? Now you can find sodium and you can find chlorine, but you have to add those atomic masses together, and then you'll know that you have a mole of sodium chloride molecules. Okay, so let's go back and just real quick look at the math behind just one of these. Okay, let's look at magnesium. How do I know if I've got 1 mole of magnesium? All right, I need to go to the periodic table, and if I were to measure out 24.305 grams of magnesium, then I know that I have exactly 1 mole of magnesium. All right, what is that equal to? That's equal to 6.02 times 10 to the 23rd atoms. All right. Well, again, if I'm looking to use and have no waste, if I'm looking to use up my magnesium and my hydrochloric acid, I know I need twice as much hydrochloric acid as I did magnesium in order to make this reaction complete. Okay, so when I look at hydrochloric acid, well, I need to go to its 2 parts. Hydrogen, which is 1.0079, all right, and 2 chlorines, I'm sorry, right here, 1 chlorine is 35.453. All right, when I add those up, give me a second. I should just say 36.5, but we get 36.46, all right, grams HCl, okay, and that equals 1 mole of HCl, and that equals 6.02 times 10 to the 23rd, but not atoms, but molecules of HCl. Okay, why not atoms? Well, it's that many atoms of hydrogen and that many atoms of chlorine, but together it's a molecule. Okay, so if I measure out this much magnesium and I measure out this much hydrochloric acid and I combine them, I'm not going to go ahead and get, I'm going to have something left over. All right, I'm not going to get a complete reaction, and the reason is look at the reaction. It says you need 2 parts of this. All right, so I need twice that amount, and if I do, if I have exactly twice this to 1 part of this, then I will use up all my reactants and I'll end up with a completed reaction. I'll know that I've got this much hydrogen gas and this much magnesium chloride at the end. And so that's all, that's kind of why we've introduced the mole. That's why we've introduced counting atoms, all right? It's so that we can go back to a balanced reaction and look at ratios, look at how much of this and how much of this is going to produce so much of my products, all right? It's so that we don't have waste, or that we have enough of each, okay? It's so that we don't walk in blindly and just mix so much of this and so much of this and hope for the best, okay? That thing over there stinks to high heaven. There is still hydrochloric acid in there. I didn't use it all up, okay? I didn't have near enough magnesium to use up the hydrochloric acid inside the test tube. So, you know, it's not safe, it's not good practice, it's not chemistry to walk into a reaction and just put stuff together and see how much you make. You know, there's math involved, there's numbers, there's moles, okay? And so we're gonna take the next couple of weeks and dive in a little bit more. But